Okay, so yesterday we were discussing reduce scatter, right? And in reduce scatter, the last algorithm we were discussing was on a 2D mesh, right? So we were considering 4 by 4 setting, total of 16 nodes, and we wanted to do a reduce scatter. So what does that mean? That means that initially there was an array 0 to 15 available on node 0, right? I'm picking node 0 arbitrarily. Everybody has 16 elements in the beginning, indexed 0 to 15. And at the end, I want the sum of all the 0th elements to be available on node 0, the sum of all the first elements to be available on node 1, and so on, right? So how did we do this? So let's quickly revisit that, right? Because what we are going to discuss next is the algorithm for hypercube, and that is primarily an extension of the algorithm for mesh, okay? So what did we do? Well, what I did was, first I did communication along the columns, right? And I ensured that in each column, right, the results for indices 0, 1, 2, 3, because those are the nodes in the first row, right? So if I look at the first column, I exchange the data, I do some kind of reduce scatter such that, let's assume it's sum, right? So the sum of the elements for 0, 1, 2 and 3 index are available on node 0, okay? Similarly, we want that the sum of the elements 4, 5, 6, 7 should be available on this particular node, right? Similarly, 8, 9, 10, 11, the sum of these elements should be available over here, and 12, 13, 14, 15 should be available on this node, right? But remember, this is only communication happening along the first column, right? So only these columns are exchanging their data, but they are ensuring that once they exchange their data, the summation of 0, 1, 2, 3 is available over here on the first node, right? So what we are having over here eventually is partial sums, right? Partial sums of the elements 0, 1, 2, 3 available on node 0. This is not the sum across all the 16 nodes. This is only sum across 4 nodes, right? Which 4 nodes? 0, 4, 8 and 12, right? Okay. Similarly, what do we do in the second column? In the second column, again, we ensure the same thing, that the sum for all the elements 0, 1, 2, 3 is available on node number 1, right? Sum for 4, 5, 6, 7 is available on node number 5, right? Sum for 8, 9, 10, 11 is available on 9, and sum for 12, 13, 14, 15 is available on 13. And again, this is only partial sums for this particular column, and so on, right? Third column, similarly, you exchange the data. Fourth column, similarly, you exchange the data. Now, what's the crux? Well, the crux is that this particular node has the summation of 0, 1, 2 and 3 for the entire first column, right? This node has the summation 0, 1, 2, 3 for the entire second column, and so on. So all these 4 nodes together have the necessary summations of their respective columns. So if I want finally for the results of 0 to be available on node 0, 1 to be available on 1, 2 to be available on 2 and 3 to be available on 3, all I need to do is communicate along the first row, that's it, right? I don't need to communicate with the other rows. I've already done that in the respective columns and exchanged that data, yeah? So I just do communication along the first row. So essentially I'm doing a reduce scatter again, right? I do a reduce scatter and eventually I get summation of 0 on node 0, 1 on 1, 2 on 2, 3 on 3. And similarly for all the rows, right? The other rows also do the same. Clear? So that's the mesh algorithm. And then we analyzed and we saw that this was what the cost was turning out to be, right? So what is this first one? This is the cost for the communication along the column, right? So if you look at it carefully, when you're doing the communication along the column, you're not doing a reduced scatter of size 1. It's not one element that is finally placed on each node, right? Root P elements are placed on each node, yeah? So therefore your size is root P times M, that's the size, right? And the number of nodes is root P. Since we are just using the algorithm for reduce scatter, right, this was the cost that we had determined for reduce scatter, we just plugged this in. The only change is that the number of nodes instead of P is root P, and the message size is M root P, right? And so this is what I get, okay? And in the second pass, what am I doing? Well, now I am doing communication along the rows, but in each row, now what is the message size? The message size is M, right? Just one element was being exchanged, right? So if you have M elements, then M elements would be exchanged, right? And the number of nodes is root p. So I again plug it into this. The only change is that number of nodes is root p, right? And when I plug that in, I get this, right? And I add this up. So what do I get on adding this up? Well, the ts terms just get added up. So 2 times root p minus 1 ts, right? Plus what happens over here? Let me take m common. So root p times root p is p minus root p. That's what I get from the top, right? And what do I get from the bottom? Plus root p minus 1 times tw, right? And if you simplify this, this is 2 times root p minus 1 ts plus m times p minus 1 tw. Okay. Now what we're going to do is, instead of 2 dimensions, suppose I had 3 dimensions, what would happen? First, I would do a reduce scatter along one of the dimensions, right? And then in the next iteration, I would do a reduce scatter in the second dimension, and the third iteration, I would do a reduce scatter along the third dimension. Yeah? And the sizes would keep on reducing by a factor of p to the power 1 by 3, right? Okay. And just extend it. So finally, what do we have? What is the extreme case? The extreme case is the hypercube.